Hi, I'm Herb Gross, and I'm reluctantly coming to lecture number 40, our final lecture in this Algebra 1 series in Gateways to Algebra. And the topic today isn't all that important other than to complete something, namely how complex numbers add to our understanding of the solutions of quadratic equations, and in fact close a little loophole that existed. But more importantly, I'd like to take the luxury of spending a few minutes with you to just sort of share with you how much I've enjoyed the opportunity to be able to have taught you this course. First of all, I'm hoping that by having the lectures on videotape, you are able to have this luxury that I wish every student could have, that we don't have in traditional education, where you don't have to move on to a new topic until you've understood the prerequisite topic. It's sad how many students fail simply for the reason that they're pushed into new frontiers before they've firmly grasped the significance of the old ones. That for some, what I'm hoping that you see in these tapes is that it's possible to hold the amount of mastery constant and vary the amount of time that it takes to learn. I hope that, naturally that all of you learned it the first time through, but I'm hoping that many of you discovered how nice it was to be able, when you didn't understand something, to review a tape, to talk over the content with someone else, and not go on until you sense what it was that we were really talking about. Because that alone will save many students and help you go on, and give you a liking for the subject that doesn't come when you're pressured by it. Secondly, and I always hate to talk about this because it sounds like I'm boasting, and I don't mean it that way, for 21 years, either full-time or part-time, I was the senior lecturer at the MIT Center for Advanced Engineering Study. And I've developed calculus series that are used all over the world. As we speak now, over 50,000 students on 5 continents, engineers, technicians, scientists, have either learned or reviewed calculus based on my 88 videotapes and 17 volumes of study guide that were developed through MIT and done exclusively by me. I'm hoping that my 40 years of teaching experience allowed me to extract from this vast field of mathematics precisely those things that not only made the subject more interesting for you, but which zeroed in on those topics that are very, very important, that come up over and over again, and yet seem to give students a great deal of difficulty simply because the groundwork wasn't properly prepared. What I'm hoping is that not only did you learn from this course, but as you review the tapes, each time you look at them, something new will come up, and that eventually you will start to get the feeling that you really do understand mathematics. And that's important for a couple of reasons. You see, once you understand something, and once you like it, no one can ever take that away from you again. You may not like a particular teacher, you may not like a particular topic, but once you understand how to learn on your own, and why you want to learn, you're going to do that. I learned a very valuable lesson from one of my sons who was an excellent football player. For 8 years, he went to what they call double sessions every August. Every single day in August, he went to football practice twice a day in that blistering heat. But if I asked him to mow the lawn, he always told me it was too hot. And it used to bother me until I suddenly realized that he was telling the truth. It was too hot to mow the lawn, but it wasn't too hot to play 6 hours of football a day. And the reason was he enjoyed playing football. He didn't enjoy mowing the lawn. The lesson is that the difference between work and play has nothing to do with the degree of difficulty, only with the degree of enjoyment. And so when you enjoy something, it's not that it's easy, but it becomes an exciting challenge. And I hope that that's the level you've reached in mathematics. I hope that your academic self-esteem has been increasing. Because after all, self-esteem is something no one can take away from you without your approval. If you feel good about yourself, you're going to perform well. And every time you perform well, it sets a standard for performing well the next time. And hopefully the tapes created an atmosphere of calm where you felt you could watch them wherever you wanted. You see, it's my belief and the philosophy of this program that if the material is made relevant to the student, if the delivery system allows students to learn at their own pace so they never fall behind and get victimized simply by not being able to study fast enough, and if the environment is fun for learning, then a very, very meaningful experience has taken place. You see, except on Star Trek, time is not reversible. If you said to me, Professor Gross, I hated this course, give me back the money I spent for it. If I'm a wealthy man, I could give you back triple the money you spent for it. But if you say to me, I hated this course, give me back the time I wasted, I cannot give you back that time. You can never have that time back again. In anything that you do, that time is gone forever. And all you can ask for productive life is that for those moments that you can never have back again, did you get enough out of it to make the trade-off worthwhile? And from my point of view, it was a sheer delight to be able to present these lectures to you. I hope that we'll have other courses in time to come that will allow you to continue with me beyond the scope. Hopefully, I will have in due time a series of self-contained, self-paced, individualized, single-topic modules that will go from pre-arithmetic through calculus, and you can hook in and hook out wherever you want in the sequence. And it was just a delight for me, and I hope you enjoyed it. And now, having said that, let's turn our attention to the last topic in the course, and that is to apply our newly discovered real imaginary numbers, the complex numbers, the directed lengths in the plane, to seeing how no longer are there no solutions to certain quadratic equations. And to do that, let's simply illustrate that with the equation x squared plus 1 equals 0. Remember, before our excursion into complex numbers, the argument went something like this. If x squared plus 1 is 0, that says that x squared is negative 1. And since a square of a real number can never be negative, it means that there are no roots to this equation. And what we showed was that if you graph y equals x squared plus 1, the lowest point on this graph occurs when x is 0, at which point y is 1. And since the lowest point is at 0, 1, that's the lowest point, then this parabola never comes down to meet the x-axis. However, since our excursion into complex numbers, we have found that there is an answer to this problem. We have discovered that the number I, for example, has the property that its square is negative 1. Well, what was I? I is the number that's 1 comma 90 degrees. Let's apply this and see what happens. Let me see if I can make this look clear to you. I start with his I. His I. Now, what will I squared be? I squared means what? Multiply 1 times 1, add 90 to 90. That brings you down to here. This is I squared. Now, add 1 onto I squared. 1 is the vector that goes, we're going to put it at the tail of negative 1. It goes from here, 1 unit. Where does that wind up? It winds up at the origin. What this says is, if you start with I and you square it, that brings you back to negative 1. And if you add 1 on to negative 1, you come back to 0. There is nothing imaginary about this solution. We're taking this vector. Okay, let's just summarize it again. We're taking this vector, we're squaring it, that brings it over to here. Then we're adding on 1, that brings us back to here, and that happens to be the origin. And we can do this with any case where we were getting so-called imaginary answers before. Let's look, for example, at x squared minus 2x plus 5 equals 0. And let's try to solve this by the quadratic formula. In this case, what happens? A is 1. Minus 2 is the same as plus negative 2. So b is negative 2, and c is 5. So if b is negative 2, the opposite of b is 2. B squared is 4. A times c is 5. So 4ac would be 20. And 4 minus 20 is negative 16. So we have what? 2 plus or minus the square root of negative 16 over 2. Now the square root of 16 is 4. The square root of negative 1 is I. So this number is what? 2 plus or minus 4i over 2. 2 is a common factor of the numerator and the denominator. So we can cancel the 2 from the numerator with the 2 from the denominator. And what are the roots of this equation? 1 plus 2i and 1 minus 2i. Let's just look at the root, 1 plus 2i. And what must happen here? If we square 1 plus 2i, and then we subtract 2 times 1 plus 2i from that, and then add on 5, the answer should be 0. Let's do it algebraically first and see what happens. I start with 1 plus 2i, and I square it. This gives me 1 squared plus twice 1 times 2i plus 2i squared. That gives me what? 1 squared is 1. 2 times 2 is 4. That's 4i. 2i times 2i is 4i squared. I squared is negative 1, so 4i squared is 4 times negative 1. That's going to be negative 4. So this becomes 1 plus 4i plus negative 4. 1 plus negative 4 is negative 3. So we have what? Negative 3 plus 4i so far. And by the way, you can't combine the 3 and the 4 because the 4 is modifying I, but the 3 isn't. So far we have this term over here. Now remember, x is 1 plus 2i. We multiply it by negative 2. Remember what the equation is. It's x squared minus 2x plus 5 has to equal 0. So if x is 1 plus 2i, multiplying it by negative 2 gives me negative 2 plus 4i. And now I have to do what? Add on 5 to that. So what do I have altogether? I have negative 3 plus 4i plus negative 2 plus negative 4i plus 5. And what happens now? Negative 3 plus negative 2 is negative 5. Negative 5 plus 5 is 0. That drops out. 4i and negative 4i, that drops out. So this thing really works. The problem with this, I would say, if there is a problem, is that people will look at this and they'll say, it's just numbers. It doesn't make any sense to me. I mean, you can square 1 plus 2i, but I don't know what it means. It doesn't make any sense to me. I don't understand this I business. So let's go back to the geometry again. 1 plus 2i simply means the vector that starts at the origin and goes to the point 1 comma 2. Can't I express that in polar form? And in polar form, there's a very simple interpretation for multiplying. That all you're going to do is what? You're going to multiply the magnitudes and add the angles. So let's try to do that. I don't know how good this will come out because I don't draw very well, but let's take a shot at it. X is going to be what? 1 plus 2i. So starting at the origin, we go 1 in the real number direction, the x direction, and then 2 up. Well, if this is 1 and this is 2, by the Pythagorean theorem, let's call this question mark. Question mark squared is 1 squared plus 2 squared. That's 1 plus 4, which is 5. So if question mark squared is 5, question mark must be what? The square root of 5. Okay? This is the square root of 5. So now what do we have? This is the square root of 5. Of course, I don't know how to measure this angle, but the slope is what? It's 2. So you're going 1 over and 2 up. Can't I take my protractor and as an approximation measure that angle? I take the protractor, I measure that angle, and it comes out to about 62 degrees. So what is x now? In polar form, the distance from O is the square root of 5, right? And the angle is 62 degrees. Now, what happens when I multiply this by itself? To get x squared, what am I going to do? I'm going to do what? I'm going to have to multiply the square root of 5 by the square root of 5. That's going to give me 5, right? Okay? And then I have to do what? Add 62 to itself. That's going to be 5, comma, 124 degrees. And by the way, again, you can compare that. See, what's interesting is what should happen with this. If we took 1 plus, see, did we take this before? Let me just check something again. Didn't we take 1 plus 2i and square it in Cartesian coordinates? And when we squared it, what did we get? We got 1 plus 4i minus 4. See, because 2i times 2i is 4i squared. I squared is negative 1. So this point came out to be what? Negative 3, okay? Negative 3, comma 4. And what would happen is if you drew this accurately, you should be able to see what? That this point, which we called 5, comma, 124 degrees, is what? It's 3 units to the left of O, and it's 4 units up. Anyway, what's the next step? We multiplied x, this vector here, by negative 2. Now what happens when you multiply by negative 2? Negative 2 is 2 comma 180. So what that's going to do is that multiplying by 2 is going to make this vector twice as long, but multiplying by 180 is just going to reverse the sense of this. So starting over here, what are we going to do? we're going to draw a vector in this direction that's twice as long as this, and lo and behold, if we take x squared and add this vector to it, where do you think it ended? It ended at the point negative 5, comma 0. And when we now add 5 onto that, where do we wind up? Right at the origin. And you see what's happened now is that even though these numbers are unfamiliar to us, in much the same way that it took us a long time to get used to fractions after all we knew were whole numbers, it's going to take us a long time to get used to complex numbers, directed lengths, after we're used to just what we called real numbers. But you see what happened over here? Here's x squared. How does it work? I've doubled the angle and squared the magnitude. I've added on negative 2x. How did I do that? I doubled the length and reversed the sense. Then I added on 5. You see, in general, what happens is if I have the parabola x squared minus 2x plus c, how many real roots I get depends on the value of c. In other words, if I complete the square over here, look what happens. See, I add 1 and subtract 1. This gives me x squared minus 2x plus 1 plus c minus 1. This is x minus 1 squared plus c minus 1. The curve is the lowest when x is 1, and when x is 1, y is equal to c minus 1. Well, if the lowest point on the curve occurs when x is 1 and y is c minus 1, if c minus 1 is positive, the curve is going to be above the x-axis. See, it's going to be something like this. If c minus 1 is 0, the curve touches the x-axis, and if c is less than 1, you're going to get two real solutions. The part that's interesting is, take the parabola where the vertex, meaning the lowest point, is below the x-axis. Okay? So now here are the roots over here. Now what's interesting is, as you move this parabola upward, watch what's happening to the roots. Aren't the roots moving in closer and closer together? And by the time the parabola is just touching this axis, the two roots have coincided. In other words, the roots on this side are moving in here. On this side, they're moving in here, and they coincide over here. Now, when this parabola gets up above the x-axis, you can't see any intersections, but a very neat thing happens. The same way that these roots came together here, as you now move this up, those same two roots separate along the line x equals 1. In other words, in terms of a geometrical picture, there is no difference between the real situation and the non-real situation. If I had computer animation here, what you would see happening is I would take this parabola, I would start to move it up, and the animation would show these 2 points moving towards each other. And when they finally collided, they would then leave and move along what? The line x equals 1, going on their own merry way, just as geometrically real as when the intersections were on the x-axis. Now again, there's no guarantee that you're going to find a place where this is practical, but that happens all the time. You see, something that makes sense may be too far advanced to make practical sense at some point in time, but maybe at a later point in time, you see, the thing will make sense. When a subject called matrix algebra was invented by a man named Hamilton in 1850, he wrote in the dedication of the book, "Here at last is a branch of mathematics that is so pure that application will never be found for it." And the amazing thing is you cannot do anything in discrete mathematics, which is a very big field in mathematics today, without a tremendous knowledge of matrix algebra. Matrices have revolutionized many algebraic concepts. And yet at the time that it was invented, what was the dedication to the book? Here at last is a branch of mathematics for which there will never be found practical application. The mathematician Samuel Eilenberg, who was a famous topologist, a pure mathematician, was also very gifted in solving practical problems. And every time during World War II, at that era, when there was a very important problem for the nation to solve, Eilenberg was always invited as one of the consultants to solve the problem. And he would always be very productive. And after he would solve the problem, people would say to him, "Sam, you're such a brilliant applied mathematician. Why do you dabble in pure mathematics?" And his answer to me was absolutely magnificent. What he said was, "I compare myself to an aesthetic tailor. Sometimes I make jackets with 42 sleeves, 53 legs, and 47 colors. But every so often, I make a traditional jacket with 2 sleeves, 1 color, and no legs. And if a fellow human being comes into my tailor shop and tries on the jacket and it fits and he likes it, I give it to him as a present from the goodness of my heart. Think of how many things that we do for enjoyment that have no practical value. And if after a while those enjoyable things do have practical value, that's something that becomes both nice and necessary. We really doubly enjoy that. And what I'm hoping is that you are reaching that stage where you do not get frightened and locked into just studying for exams, but stepping back from some of these topics and looking at them and saying, my gosh, it's amazing what the human mind can do. And as you gain these experience in the subject, I hope that the logic that you learned will help you apply it to other subjects. That you will see, as I think I may have mentioned earlier in the course, that algebra is the calisthenics in the game of logical thought. In the same way the football player does push-up after push-up after push-up, but never uses a push-up in the game, but rather uses what? The skill and the strength that those push-ups gave him. In real life, we don't often use algebra per se, but what we do use is what? The improved logical skills, the improved insight, the improved ability to see things abstractly, to see life in all of its glorious colors rather than in dull pastel shades. That's what education is all about. And as a friend of mine and teacher once told me, he said, Herb, when you've forgotten everything else that you've ever learned, what's left is the only thing you have a right to call education. Don't worry about what you remember today. It's too soon. The real test will be, what do you remember a year from now? What are you doing a year from now? And don't compare yourself to other people, but try to imagine a year from now, wherever you are, where you might have been if you hadn't had the courage and the confidence and the persistence to master this course. So in closing, let me wish all of you good health, great happiness, much personal fulfillment. God bless you all. This has been a real pleasure. Until next time.